My background is I have a bachelor's in geology from Cal State Northridge, and worked as a geologist for a couple of years in geology. Realized I was far too immature for a real job and became a fireman. Did that for 25 years, and then my body said, you can't do this anymore, and I retired. I didn't do any real geology for most of that time, so all of the good stuff that taught me in 4 years of intense instruction has pretty much been forgotten. And what we have left, I can squeeze into the 2 hours that we have. So that's all you're going to get. The thing about geology for me is I was working as a wilderness guide, wilderness instructor for the school, and when we were walking through the Sierra Nevadas, people would go, what's that? And then I'd say, I don't know, it's a rock. So I took a geology class. In that geology class, I approached it with great trepidation because everything I knew about geology was memorize 200 rocks, memorize 200 different time scales, memorize 200 different fossils. And I'm terrible at memorization, so I was going, this is going to suck. Okay. And then I got into the geology class, and this little thing called plate tectonics took geology, which was just random events in the history of, let's say, the Appalachians. They'd go, the sea came in, the sea came out, the crust got crunched, mountains came up, mountains got worn down, and then it happened again. And the question was, why? Don't know, it just happens. And they call it the geosynclinal process, but nobody knew why it happened. Well, when you understand plate tectonics, now we know why it happened. 2 continents went bang, and that's what caused things to crash together. And then they started explaining, well, how do you know that? Well, the density of this rock is different from the density of that rock, and da-da-da-da-da-da. I'm going to spend 2 hours now giving you that framework that makes geology make sense over time. Okay, and that's about all we're going to get. You have a little cheat sheet. It is, most of it's going to be subject to test later on, but you do want to pay attention. But we're going to review it at the end to make sure that you have what's important. You're going to end up with 3 names for kinds of rocks, 3 different names for rocks. I can get you some more handouts. Okay, so we're going to have names for rocks based on how they're formed, names for rocks based on what they're made out of, names for the 4 major time periods through geologic history. And so it's pretty simple stuff, and it'll make sense as we go forward. Okay. When I think about geology, the thing that helps me become a geologist is processes rather than memorization. So a lot of what we're going to work on today, come on, there we go. What we're going to work on today is not memorization, it's understanding the processes that make the world work. And those processes have not changed over time. So stream channels are shaped like a V. Glacial channels are shaped like a U. Okay? Those processes have worked the same because physics works the same over time. And it works over a long period of time. The things don't happen very quickly unless you're going to talk about perhaps climate change. Okay, process over memorization. Okay, the things that you're going to get off your list are sedimentary, metamorphic, and igneous rocks. Everybody heard those before? Yeah. Okay. Feldspar, quartz, mica, and calcite. Now, everybody heard of those? Okay. Somebody here's lying, because most of us have not. Okay. All right. And then those are the most common minerals that we're going to talk about. And then the next one down is rocks based on what they're made out of. Granitics, conglomerates, gneiss, and limestone. Those are the rocks we'll find here. We're going to go for a walk later, and you'll all be able to point out, yes, that's conglomerate, that's a limestone, that's a granitic. And then faults. Earthquake faults define life in Southern California in many ways. How many people here have 3 days worth of water in their house. Okay, those are people who've heard my lecture. You all know what we're done. Okay. The other thing that I have done for many years is teach community emergency response training. And that's based on the fact that the fire department is not coming after the big one. You are going to be on your own. And if you don't learn any of this and you get water in your house, your time will have been well spent. Okay? I am a firm believer in smoke detectors and water for earthquake preparedness. So we'll come back to that later. All right, so the processes that brought everything together, like I mentioned before, is plate tectonics and the rock cycle. As the surface of the earth goes sliding back and forth across the mantle, crashes into different places, gets subducted, the rocks get moved, put into environments, and changed. And the rock cycle is what makes that all happen. Okay, so this is our home. It's got an inner core, outer core, mantle, and the crust. In this picture, you can see the crust. If it was to scale, you couldn't even see it. The crust is divided into 2 main types. There's a crust where it's a continental crust and a crust in the ocean. The ocean crust, oceanic crust, is only about 5 miles deep. And then you're into mantle. It's about 70 miles deep underneath the continent. All right, so rock names. I got ahead of myself. Sedimentary, metamorphic, and igneous we already talked about. And then when we talk about what it's made out of, this is chemistry. Anybody like chemistry? Okay, you guys can help the rest of us with the chemistry. Okay. My daughter is about to graduate from Cal State Northridge. Somebody asked her what, a year and a half ago, what's the coolest thing you've ever seen? And she said the periodic table. I read the nerd. You don't have to learn the periodic table. There are just going to be a few atoms that you have to figure out in order to get through it. All right. That's for sedimentary rocks. That's kind of out of order. We're going to come back to it. Okay. Igneous rocks. The way to remember, first way to remember the names of the rocks or how they form. Sediment settle out. So you've got stuff that's either being carried by wind, water, or glaciers, and it drops out and stops and gets buried and becomes a rock. That makes it a sedimentary rock. Igneous rocks are things that have melted to the point where it's one homogeneous broth of stuff. Okay, so the way I help people remember it is igneous is so hot it would ignite things. And this is lava off of a volcano, and we're used to seeing that. This, when it's flowing like this, it's what we see out of the basically coming straight up from the mantle like we see in Hawaii. It's called extrusive. This stuff gets outside and it cools so fast that it doesn't get to time to form crystals. If it is inside the earth as it cools, then small crystals grow, and we'll come back to that later, and you get rocks like we see in the Sierra Nevada. In between the two, settles stuff that can settle out, you still see the particles, stuff that melted all the way and is coming out of a soup, you have metamorphic rocks. Okay? So when we talk about, and this is obsidian, we don't have much of it around here, but it's a common rock that people will see. This is an intrusive igneous rock. In this case, it cooled so slowly that the individual crystals of different kinds of minerals had time to form and separate and within the earth. All right, and there's the in-between rock. You guys have seen the fancy rocks that are on the that they transport out and that are on the chimney. This has some limestone and some other stuff, but that's obviously been smushed. Okay. All right, so how does our world get built? Big Bang, suns. Everything was helium. This is vastly simplified, but it'll work for us, for what we don't need to know for making this class work. Okay, everything is helium, and then suns form, get super hot, we have cold fusion. This is not something you need to memorize. This is the framework that helps it all hold together. Okay. Inside the suns, we have fusion that creates a bunch of heat and energy. Hydrogen gets together and becomes helium. Heliums get together, a bunch of those become carbon. A bunch of those get together and become nitrogen. And it keeps building atoms. So everything around us that isn't helium is a result of a previous star doing its thing, blowing up, scattering its molecules around and atoms around space, recombining, and voila, here we have our planet. Okay? So atoms are the simplest thing. An atom is defined as the simplest, smallest particle where you can define physical characteristics of that product. So oxygen atoms are different from helium atoms. Make sense? Doesn't anybody yet? Okay, the one other thing I forgot to mention is that I will occasionally get so involved in what I'm trying to tell that I will lose track of what I'm saying, and it becomes very confusing. Please, do your friends a favor, stop me. I'll back up to the place where I stop speaking English, and we'll go on. All right? So, atoms are simple. When you get all atoms of one kind, all, let's say, silicon, together, and it's just silicon, that's an element. Okay? Some of the items in the kinds of atoms that are in the periodic table are solid at room temperature. Some of them are gaseous. But when they combine with other things, then they may all become solid at one time. So, atoms of all one kind of atom, let's say that we count the number of protons in an atom to tell what it is. So, all the same atom is just an element. When we start to mix atoms from different, mix atoms from different elements together. So we have, let's say, oxygen and carbon. They get mixed together. Then those will form a molecule. When you get a bunch of molecules that come together and they arrange themselves in a special proportion, they become minerals. When you get a bunch of minerals that are now mixed together, those become rocks. When you get a bunch of rocks together, they become landforms, and then we get to earth processes. Okay, really fast, kind of confusing. Anybody feel too lost to go on? All right, so jumping back to atoms and how they form both molecules and crystals. One of the coolest molecules that you're going to get is common table salt. Okay, and the reason it's common is because you've got sodium and chloride, and they pack together very, very well. In order for salts to form, all you really have to do is have water precipitate out. If the water precipitates out slowly, the atoms have a chance to bounce in and settle in exactly the right place to form the salt crystals, and you get good big crystals. If you took your salt water, put it on a frying pan, and boiled the water off very quickly, you wouldn't have big crystals form, you'd have lots of little ones. Okay? In the earth, we get the same sort of thing happening. Inside that big magma chamber that used to be underneath the Sierra Nevada, we had a mix of a bunch of different chemicals that were all trying to find a place to settle in as it cooled. If it's hot, then things are bouncing around and it's a liquid. As it cools, they become solid. As it becomes solid slowly, the atoms have a chance to get into their preferred least energy orientation, like this, and become a crystal. Okay. So one of the things that you see in a crystal is the orientation of, the proportion of the atoms. For this, it's 1-to-1 sodium and chloride. For other minerals, it'll be something else. But you also look at how the minerals pack. When I was in chemistry, the chemistry teacher said, geologists are all crazy. They not only have to remember what the proportions are, we have to memorize what the orientation of the crystal lattice is, out of, 9 different types of crystal lattice, and how the light goes through that and gets refracted and all sorts of stuff. And pretty tough to get through those 4 years. But when you do, you can bore people to death. Exactly what my wife is geologist do. Just a question, yes?
So the definition that you just gave us of how minerals clump together, would that then explain why you would have veins of gold or silver?
Okay, everybody hear the question?
Yes.
Okay, and the answer is, good thought, no.
Oh.
The veins of gold and silver we'll come back to later, but basically it's because you have solid rock and cracks in it, and the fluids flowing through those cracks now are bringing new elements, usually things like water, copper, gold, silver, iron, and as those are flowing through the crack, they have precipitation that drops out the minerals, and that's where the preferential location of the ores are. Okay. All right. So we got sodium chloride. Wandered a little bit more behind, so I'm not going to do my demonstration. But if you notice, the sodium chloride here is a cube. You can do an experiment where you can fill out table salt and then put I'll show you what's going to happen if I'm not. Okay. Salt, table, rounded edge. You put enough salt down here, it creates a pile, and then you can put this down into the pile of salt, and it will balance. And the reason it'll balance is that you're creating a little structure where all of the square shapes build a solid foundation for your thing. I'm not going to do that because it makes too big a mess. But trust me. Okay, so talk about crystal structure. We see crystal structure. We hear about it in snowflakes. Every snowflake is unique. Okay, so we don't have to worry about that. Our geologists don't have to worry that hard. We deal with a slightly simpler world. Okay, so let's get down to what's the world made of? What's the primary component? It's going to be silicon, oxygen, and a bunch of other stuff. Silicon and oxygen, when they come together, form the silicate tetrahedron. 1 silicon, 4 oxygen. You don't have to know this. What you do have to know is that it tends to form this tetrahedron, which is like a pyramid. And then these pyramids are the building blocks of the silicates, which are the primary kind of rock on Earth. Remember before we had silicates, carbonates, and evaporites? Silicates are the main thing. This, when you get silicon, or silicate, tetrahedrons, and you get a bunch of them that have a chance to slowly form a crystal, it'll look like this. Okay? Those crystals have a couple of characteristics that we're interested in. The first one is the orientation of the atoms and how they stack. Very important when we look at mica. The next one is, what's the surface of the crystal look like? And the third one is, are there any places in this where it's weak and it tends to break? Okay? So, if that's what silicate, pure silicon and oxygen get together and form silicate tetrahedrons, the tetrahedrons form quartz. Okay? Quartz crystals look, I'm sorry, that's not a great picture. You've all seen the quartz crystals where it's 6-sided and it's got shape. Okay? That's a crystal face as it forms. The thing that makes quartz easy for us to recognize in the field is even though it may change color based on the contaminants that are in it, a little bit of copper changes one color, a little bit of magnesium it changes to another, doesn't matter. Quartz, when it breaks, is not going to have a cleavage plane. It looks like glass. So if you're looking at a rock, and rocks have a mixture of things in them, and you see a crystal that's whitish, you go, okay, is that quartz or feldspar? We'll get to feldspars in a second. If it looks like broken glass on the surface, that little crystal is quartz. Okay? All right, so hard, durable. The white sand at the beach is mostly quartz. We're going to walk out there today and we're going to see new beach being carried down to the ocean as it goes past us. And you'll see why.
Hey, Eric,
Yeah.
just one question on quartz. There was an article on the internet, so it had to be true, within the past couple of months about this. I think it was in Mexico, or was it China? I don't know. These gigantic, humongous, like quartz crystals. Did you
Yeah.
see that at all? And if you did, is that real? I mean, these things are like as big as this room. I mean,
I didn't see it.
Oh, okay.
It is possible.
Okay.
Was it in this cave?
It was in a cave. Yeah. Did you see that?
I've heard of it. I'm not sure if it's quartz, but it's in this cave, which is actually in New Mexico in the U.S.
Okay, I thought it was cement, but it could have been. Yeah, but they were gigantic.
Yeah.
I thought it was quartz, but I've never seen the crystals that huge. I mean.
They'll get bigger and bigger and bigger depending on how long they stay undisturbed.
Okay, so they can get huge.
They can get huge. Okay, it depends on how long they're undisturbed and how much contamination comes in. Okay, so if we start out with pure silicon and oxygen together, and that forms quartz, the next thing that happens is we start to pour in contaminants into our mixture of what the lava, the magma that's inside where it's going to form. Is we pour in some calcium, sodium, and magnesium. Don't worry about it. Some other stuff comes in and it messes up that simple, perfect tetrahedron that we saw before that forms quartz, and we get feldspars. Okay, you can have 7 different kinds of feldspar depending on the proportion of calcium, magnesium, and whatever that's in it. We don't care. It'll change some of the characteristics of how much of this lining we see on it. You don't care. All you have to know is if it's not quartz and it's white and got flat surfaces on it, it's a feldspar. That's important. Feldspar is the most common rock on the surface of, common mineral on the surface of the earth. Okay, so if you pick up a white rock out here, or one of your kids does, and says, "What's this?" Without looking, if you say feldspar, you're probably right. If you look and it's got glass-like breakage on the surface, it's quartz. So voila. Yeah, see, you did learn something. All right. So if you look in your boxes as we go forward, 1 and 2 are different kinds of feldspar based on that contamination level. And if you take those samples, rotate them, and look at the reflected light on the rock, you will see a flash of a clean surface like a plane of glass. Okay? Even though it's not all on one surface, that's because the cleavage planes are going to break that rock as it goes down, all in the same orientation. Yes?
I can identify rock of feldspar and rock of quartz. But when it gets mixed up in granite or something, how do you then tell the difference between feldspar and quartz?
It's going to have the same characteristics. That little crystal of quartz inside the granitic rock is going to usually be grayish rather than whitish, and it's not going to have a surface plane. The feldspars tend to be, but are not always, more of a lighter color, and they will have cleavage planes.
So if it shines, it's feldspar.
If it shines like a sheet of glass, it's a feldspar. If it shines like a sheet of broken glass, it's quartz. That's the way you tell them apart. Other than that, the strength of the material is basically the same. Okay? All right. When you talk about kinds of rocks, jumping back to igneous, metamorphic, and sedimentary, if you can see the grains of the material and they are separate, that's a sedimentary rock. If you can see the crystals and they are intertwined, then that's either an igneous or metamorphic rock, because the crystals have grown and changed. Make sense? Okay. All right. The next mineral that we're going to try and identify, the one that's easy, the one we see a lot around here, is a mica. There are 2 different kinds of mica. One is called biotite. The other one's called I forget, it doesn't matter. Biotite is black. Okay? We don't care. If you hear somebody says, "Is that a biotite?" You go, "Okay, great." But if it's really flat and shiny, it's a mica. It is a common mineral inside granitic rocks. So that's the other thing that'll flash. The reason this stuff flashes, the orientation of the crystals, excuse me, the molecules inside micas are all in flat sheets. So it's really easy for it to break. That means that the micas break down very quickly during weathering. They turn into clays and make it hard for you to garden. But in the streams, you'll see little flakes flowing along. Those are micas. All right, and now we get to the rest of the 2,000 minerals, 200 of which you have to know to get out of your mineralogy class, and we don't care. They're not all that common, and you don't have to know them. We can find a way to tell people about it based on the chemical composition, and it comes down to if the stuff has mostly feldspars and quartz, and not many other contaminants, then it's what we call a felsic rock. If it has a bunch of other things, iron, magnesium, and such, then it's called mafic. Okay, this gets important later because the darker minerals are heavier, the lighter colored minerals are lighter, and that is going to help control subduction and such when we get to plate tectonics. Okay, so if somebody asks, what is this rock? And it doesn't have much core, you can see gray is your quartz, white's your feldspar, not much feldspar or quartz in this stuff. In your boxes, that's the augite and hornblende are the two most common of the dark minerals. Learning how to identify those is for another class. But if it's a dark mineral and it's a silicate, then we just call it mafic, and that allows us to talk about it. Okay? All right. The reason that's important is those mafic minerals, amphiboles, you have examples of many of these in your box. Amphiboles, pyroxenes, hornblende, augite. Those are the minerals that are most common inside the mantle. So the lava that's coming up in Hawaii, straight out of the mantle and onto the surface, it's also what gets pushed out at the spreading centers in the center of the ocean. Chemically, it looks like this stuff. Okay? These things break down, weather easily because the leaching of minerals out for plant life and such attacks these preferentially. But it's heavier, it's denser, and it's found in oceanic crust, not in continental crust. Make sense? That'll come up later. Didn't mean to do that.
Oh, you hit the wrong button. There you go.
Okay, so what's the world made of? What's the most common kinds of rocks? Okay, plagioclase, alkali feldspar, those are both feldspars, and that makes up over almost 50% of the surface of the Earth. Okay, and we have quartz at 12%, pyroxenes and amphiboles are next, but that's only 16% of the rock you're going to see out there. And you can just say mafic to describe those. Micas, which then turn into clays when they weather, and everything else. Okay? That's just the silicates. We also have stuff that's made out of carbonate, like limestone and evaporites, which are present but not very common. So, carbonates and limestone.
Eric, when you say I have a sandy soil, that would be more silica. I have
When you
a
say
clay
sandy soil, it refers purely to the size of the particles that are in the soil.
It has nothing to do with
It may be
silica.
because you have mostly quartz and such in the soil, but if you're describing a soil as sandy, it's because it has more sand-sized particles than clay-sized particles.
Okay, so clay soil is not necessarily mica.
Clay soil is the clays that are in the soil are weathered mica that is broken down to form clays. Okay, so the next kind of rock is carbonates. This is where what we get from coral reefs, like the Great Coral Reef. During long periods of the history of the Earth, the entire center of the United States was filled with coral reef type environments. Not exactly coral, but something close enough for our discussion. And so the calcium carbonate, calcium and carbon and oxygen mixed together, and it usually is brought in by animals that turn it into shells. And then those tons of shells become the rock over time. The other place that you see it, and we'll see some of these in rocks near here, is if you are in a desert environment, calcium carbonate preferentially evaporates out, and it'll form layers in the rock, where it's calcium carbonate layers. Not good for gardening. That's part of the reason that people, societies that have used a lot of irrigation in an arid environment don't get to stay where they are for thousands of years. It gets too salty and soil is dead. Okay? All right, so if it primarily forms like this by animals, that's how it gets pulled out of the atmosphere and turned into a rock. How does it become this, which is limestone as a crystal? This is called calcite. It's in your book, in your box. It is a fuller, and it looks very much like quartz or a feldspar. The difference is two things. One, the angle between the cleavage planes is different, which is kind of hard to tell if you haven't practiced. And if you put vinegar on it, it'll fizz. That one anybody can do, if you have vinegar with you. Okay? When you look at our fancy rock, a lot of the twisted gray stuff is limestone. Yes?
When you said fertile carbonates in animals, what about plants?
Plants, well,
There's a difference.
yeah, there's a difference, and it's both, but it depends on whether you want to call corals a plant, and I want to stay away from that discussion right now.
But mainly animals.
Sure. It's not an important, to me, it's not an important distinction, and I wouldn't hang my hat on that in a future discussion.
I was just thinking living thing,
Yes,
organic.
source versus something sucked out into the middle of the earth. Yeah, that's a good solution, organic. Okay, so if you look at this, which one of those is a sedimentary rock? Which one looks like it's settled out someplace? With all those shells.
It's not a trick question.
It's not a trick question. Take a guess. Okay? So it can go from that to those calcite crystals if it gets enough heat and pressure. Metamorphics are a matter of taking a rock, whatever it was before, heating it up and smushing it. And that makes it metamorphic. Okay, rock types. Again, sedimentary, igneous, and metamorphic being between them. There's a trend in sedimentary rocks. We talk about those being layered. That's because if you're going to bring a bunch of stuff in and drop it, it's pretty much going to fill up in horizontal layers. Okay. Igneous rocks, this is a great example. You can see on here, we've got the mafic minerals, and we've got other crystals, and they're all intertwined because they precipitated out of a melt slowly over time. Okay? So let's pretend that you're making rock candy. Those are crystals that formed out of a solution. Okay? But when these crystals, you can pass that around. For anybody that hasn't had a chance to see those crystals, you can do this at home. Pour a bunch of water into, a bunch of sugar into some boiling water. Easier than pouring water into boiling sugar. And let it sit in the closet for a couple of days, and you'll get crystals just like that. A little bit of watercolor and a little blue. Sorry?
With a string or something.
With something to, if you don't put something to start the seed crystals, it'll just form around the exterior of the jar, and then you've created a geode. Okay? The difference is that this has basically water and sugar. Two components. One component that's going to crystallize out. In mineralogy and igneous rocks, you've got lots of different things that can precipitate out, and you spend an entire semester as a geologist learning which things drop out at which pressures and temperatures over time. We don't need to know that. All right. Okay, so here's the process that changes all the rocks from wherever we go. We'll start out with a molten earth. There's some differentiation in the different core, lower mantle, upper mantle, asthenosphere, yada yada, we don't care. The molten stuff is the mantle on which the crust slides. The crust is made up of primarily feldspars and sedimentary rocks. On the surface, most of what you're going to see is sedimentary rocks. Okay, so you've got a hill, it's eroding, comes down, turns into sediment. It keeps having more and more stuff slough off until it gets buried, buried, buried. As you get higher pressures and temperatures, as you get buried, this will slowly turn from unconsolidated sediment to a sedimentary rock. Okay. If it goes a little further and it starts to get smushed, then it becomes metamorphic. So the example I use is, let's pretend I tell the kids you're on your way to school, you leave your lunch in your car, mom goes to work, sun comes up and shines on the car, and the Snickers bar that you had planned for your dessert gets heated up to about 140 degrees. You now have a metamorphic Snickers bar. Okay? Mom comes to pick you up after school, your brother throws his book bag on top of your lunch. Now you have a metamorphic bar that's been worked over, okay? And it's hardly even looks like a Snickers bar anymore because it's mashed, but you can still tell what was in it originally. Okay? The point at which that Snickers bar melts completely and you can't tell what the original components were, and it's homogeneous, that makes it an igneous rock. Okay? Then the igneous rock gets taken out of the igneous bar, gets taken out and cooled, and it becomes solid. If it cools slowly, the crystals form like you see here. If it gets extruded onto the surface, then it freezes so quickly that only either no crystals or really small crystals have time to form. Okay? When this happens, the style of that volcanic eruption depends on the chemical composition of what happened. So if it is straight from the mantle, it's stuck the top and melts at a fairly low temperature, and it flows, like we see in Hawaii. If it's a result of differential melting, where this stuff comes down and it has more silicon in it and less of the mafic materials, it's lighter, and it becomes the composition that becomes granitics. We have granitics on the mountains to the south of us, and those are the source for most of the large cobbles that are inside our streams. Okay, the place that we are most used to seeing that is in the Sierra Nevada, and in the Sierra Nevada, this magma chamber was 100 miles deep in some places. And so the rock was coming in and it would inject a big area, slowly precipitate out. The dark, heavy stuff would end up at the bottom of the chamber, lighter stuff at the top, and the hard rock geologists go in, do chemical analyses of all that stuff, and they can tell when the pulse of the next heat wave came in and changed the composition of the rock. For us, it's a granitic rock. It's an igneous rock, and it's mostly white. It's a granitic. That's all we have to know. Okay? All right. The thing that makes this stuff a little more complex is that the rock cycle doesn't just go like this all the time. It'll get to here, and then it'll go back down. And so you'll have a rock that was an intrusive granitic rock. It gets pushed back below and melted again. And those crystals that we saw that were nicely formed, now all of a sudden they're getting elongated, and it becomes a metamorphic rock. Okay. All right, sedimentary rocks. Sedimentary rocks are cool because you can look at a sedimentary rock and tell yourself something about how it formed without doing the chemical analysis. All of us have seen the physical processes that form these rocks. Understanding those physical processes allows you to look at the rock and say, when this formed, this was a debris, a fan coming off of the mountains like we have here, and it's filling up the sedimentary basin of the valley behind us. Okay, so this was a terrestrial deposit coming off of rock mountains that were composed of such and such, and it probably traveled X distance. That's a pretty cool thing to be able to recreate just from looking at a rock. Okay, in order to explain it to the kids, sedimentary rocks are the ones that look like layer cakes. On our hike, we will walk up to the water tower, we will look to this side of the valley, and we will see sedimentary rocks. And they are laid in flat, mostly in layers, but they are not completely flat. They are tilted some. Okay. The other thing that we'll see is there are sedimentary rocks on this side of the valley that we have to figure out how they got there, and that will be part of the hike. Usually, sedimentary rocks form from below sea level because they have to not be eroded away by the next flood. Okay, that'll change if you have enough mountain building going on that enough mountain building going on that it gets buried even though you're not below sea level. You know that when you get to there, there's not much more erosion happening. That's what I'm saying. If you're in Death Valley, there's not much erosion happening, but it's for different reasons. Okay? So when we look at a river channel, you can see that there's a big wide channel that's mostly filled with sand and gravel. But right here, that stream is cutting out a small channel inside the previously deposited flat stuff. We can go out and look at the rocks, and you'll see, looking at it from the end, a round space with big rocks at the bottom, and then finer stuff above it. That's because there was a flood. Scraped it out, dropped bigger rocks while it was flowing at a high speed, and then settled down and slowly filled in with finer materials. Okay. If you see that, you know that that's the kind of depositional environment that created what you're looking at. As you drive out back to the freeway, you'll see things that look much like that. So, rock hammer for shape. This whole bed was deposited and nice and fat and happy. This flood came through. It filled in the existing stream channel, and in one event, deposited another 4 feet of mud. Okay. Anybody think of any events around here lately that have done that kind of thing? Okay. So that's a depositional environment, and we know that that was a debris flow. When you go out and look at the rocks, you'll see debris flows that are 20 feet thick. Tells you something about where you want to build your house.
What causes those
Hang on.
horizontal?
Hang on. There we go.
What causes those horizontal skinny lines?
That's a fracture, and those, given enough time, those could be the ore veins, where there was a break in the rock for some reason, and the water flowed through there and it's depositing various things. Usually in this case, because it's above ground, not deep in the earth like most hard rock deposits, this is probably mostly calcite. Calcium carbonate caused by the differential presence in the water as water evaporates. We can tell it's not the layer cake stuff because it curves through the bed. Okay. So that's footage that was on before. That's the Antelope Valley. During that flood, they had 2 fatalities, many homes messed up, and bulldozers moving things in order to get the water out. Okay, conglomerates, that's the name we use when you have a rock that has lots of fine stuff and then lots of big stuff mixed in it. Okay, out at Vasquez Canyon, Vasquez Park, you'll see conglomerates that have lots of sharp, angular stuff in them. If you look at the rocks that are near us, most of those cobbles are well-rounded like they've been in the stream for a long time. That means the depositional environment for this conglomerate was very close to its source because these didn't have time to get well-rounded. The stuff that we're seeing here got carried for a longer distance. When we talk about the Sespe Formation, the Saugus Formation that's near here, the source rock changed because of San Andreas moved us away from one mountain range and closer to another. That's part of what helped us figure out what the San Andreas was. Okay, metamorphic rocks. This is the what happens when you get it smushed because of the heat and temperature. The kinds that we're going to look at, basically it's going to depend on the orientation of the crystals. Just as the crystals have a preferential breaking orientation, they'll have a preferential formation orientation if there's pressure on them. So in this schist over here, that was a rock that had a bunch of micas oriented in any number of ways. It got smushed, and the mica, the atoms inside the micas said enough of this, and they moved and reoriented until they were all parallel. If you can see that kind of layering, and it's shiny, that's called schistosity. But basically, whoops, that's a schist, and then a gneiss is where it's banded. Here you can see where the mafic minerals, there weren't many of them, banded together preferentially, and the felsic materials, primarily quartz and feldspar, are together in bands. Okay? Again, a result of the pressure on it. And then one of the cool rocks that I have to talk about is, it's called an augen gneiss because that looks like an eye. I got my bachelor's and worked for 2 years, and then worked as a firefighter for 23 years, and then taught this class for 2 years, and finally one of our docents who speaks German said, no, you've got that wrong. Not all gneisses are augen gneisses. Only the ones that have the little eye are augen gneisses. Otherwise, it's just a gneiss. So for those of you that heard my lecture 4 years ago and I lied to you, my apologies. Okay, but if you look at the top layers of that, those dark minerals there have oriented and created some schistosity. Schistosity just talks about the characteristic. In order for it to be a schist, it has to be primarily made out of that sort of stuff. Okay, is anybody going to call you on it if it's 51% of one thing and that, you know, you're off? No. The process that got you there is going to be good enough. That's placerite of fancy rock. It's the stuff that was of economic use, and it's a pretty interesting rock. It's got some limestone mixed into it, which means that that rock was somewhere where there was the organic material was bringing out calcium carbonate. They had layers of limestone mixed in with layers of other sediment. It got pushed down and smushed and turned into rock, and then squeezed from the side, and then squeezed from the side again, and you end up with this stuff. Okay, igneous rocks. This is going to be pretty quick because we don't have a ton of it. Again, we've already talked about the fact that if you look at this sample, those crystals are interlocked because they formed in a melt, and they just precipitated out to the bottom, and then other stuff grew around it. Slower close. So when he talked about the big quartz crystals, he was talking about stuff like this. That's probably 3 inches long. You can find them in rock shops, commonly 4 to 6 inches long as a single quartz crystal. And apparently they're 6 feet long in some places.
Yeah, they were huge.
Yeah.
So I've got a witness.
Okay. But the thing to remember is that these cool faces are a result of how the crystals grow, not how they break. And that's what helps us identify which ones are quartz and which ones are not. The breakage planes, if it's got a breakage plane, it's a feldspar. Okay. This is an example of a rock. We're going to go right by it because we don't have any of it around here. It doesn't matter. Okay. Granitics. There are lots of different names for the different gradations of percentage of white stuff versus dark stuff in your granite. You don't care. Granitics. It's close enough. It's an intrusive, igneous rock of a largely felsic, it's mostly white material. And it hasn't been remolded by heat and pressure to become a metamorphic rock.
And just as a point, Eric, just for our docents, if you see, because there's a lot of stuff around here, we walk out, you'll see it, it looks like granite to me, it looks like that. If the kids ask, what kind of rock is that? Granite is okay, granitic rock is okay. it's a
Yeah,
mixture of
only
minerals.
a geologist is gonna know that that's not a granite, that's a diorite. A granite,
See, okay.
you know, who cares? So that's why if you say that's a granitic rock, then yes, it may be a granite or a diorite or whatever, but it's a granitic rock, and that gets you around. Some people worry about never saying anything that's not absolutely true. I don't, so you guys are on your own. But granitic rock gets you around that rule.
Yeah, because that's a big category of
It's
rocks.
yes,
around here.
just like feldspar includes lots of different subcategories.
Right.
Okay. If you see a truck and you go, "That's a pickup truck," you're right. It may be a Chevy Silverado 3/4 ton crew cab with 4-wheel drive, but it's still a pickup truck. Okay.
Good.
All right. So here's some of the stuff that pulls it all together. 70% of the surface of the Earth is sedimentary rocks. But the place that's not true is if you go to Hawaii, where it's basalts, and those islands are completely formed out of basalt. Some of that has broken down and weathered, and they have beaches made out of black stuff. That's still the same chemical composition, but now it's in smaller particles, so it's sandy. Okay? The most common mineral is quartz in the crust. Feldspars are the most common rock in the crust, if you include all the different types of feldspars, all the subdivision. So basically it's quartz. If you subdivide the feldspars, there's more quartz. If you lump all the feldspars together, there's more feldspar. Okay, I'm a lumper, so let's go with that. All right, so rocks that you're going to see here in Placerita Park, sedimentary rocks on this side of the park, and metamorphic rocks and granites on that side of the park. Down low where we're going to do all our hiking, where you guys are going to mostly be, it's all metamorphics. The granitics are exposed up the hill. Okay? So the big question is, how do we get sedimentary rocks over here and metamorphic rocks that form at great depth and pressure right next to each other in a contact that is basically right underneath our feet? That mystery will have to do you until we get back from our break in 10 minutes.
Great. Okay.
In that whole span of time to say when it formed, what other things were going on around it. Otherwise, it's just a random factoid. Okay, so when they started to talk about geologic time, and they realized that in order for geology to work as a science, you have to have more than 3,000 years for these processes to work. On one of my tours, I asked, leading a group here, I asked, "So, how old's the Earth?" And everybody turned to look at little Bobby, who was obviously the smartest in the class, and he said, 3,762 years. And so we just went to memorization from that point on, because geologic processes do not work in 3,762 years. Okay? So when they started to try and figure out how old things were, the only way they could do it was based on fossils. And that's why we have these names. So when you talk about Precambrian, that's the oldest period of time, and it, if you look at it right there, is 4 billion years. Why did we choose to have one time frame that's 4 billion years long? Because there were no fossils, so there was no way for us to subdivide it. The very first oldest fossils that they found were at the base of the Cambrian. Those were the trilobites. When they first found megafossils, they said, now I can start figuring things out from here. So everything older than the trilobites is Precambrian. And then everything after that, we're subdividing by the kinds of plants and animals that we see on the planet at that time. So if you were to go find a saber-toothed tiger tooth, would you think that happened 250 million years ago? 20 years ago? It happened in the age of the saber-toothed tigers were around, which happens to be Miocene, Pleistocene in the Cenozoic. So within the last 65 million years, actually for the saber-toothed tigers, closer to 200,000. All right? So that's the way geologic time is created. It was created before there was any way for us to put an actual number to the years. So the names, Cenozoic, Mesozoic, Paleozoic, and Precambrian, nobody's gonna quiz you on that, okay? But if you wanna have that in your mind to help you hold things together, the way that these divide them is basically Precambrian, there was life and there were fossils, they just couldn't find it with their little hand scopes. Once we got microscopes, then we could start subdividing the Precambrian. So before 540 million years ago, no megafossils. From 540 million years ago to 250 million years ago, basically the age of fish and some processes where animals started to come out of the oceans. But lots of cool animals back there, the nautiloids, super huge squids, all sorts of cool things. But for us, the age of fish. From 250 million years ago to 65 million years ago, the age of dinosaurs. Long run. And there's some evolution within the dinosaurs through that whole period. Mammals are actually around for a lot of the end of it, but it's primarily the age of dinosaurs. And then from 65 million years ago to the present, it's the age of mammals. Some of that's our arrogance to say that our group is the important one. Certainly we're changing the planet more than anyone else has. But that's the geologic timescale. And again, it's based on what you can see in the fossil record through that period of time. Make sense? All right. So since it was easy there, then we have to make it harder because we find more and more fossils and we can subdivide it. And this is where I lost it because I couldn't memorize those 52 things on the right. Okay? But fortunately for you, our test is easier than that. So oldest rocks in the San Gabriel Mountains are Precambrian rocks. Then you get into the middle of the Paleozoic, and that's where the metamorphic rocks that we see on this side of the valley were formed. They're metamorphic, so there's no fossils, so it's really hard to tell exactly when they were formed with that method, but you can go in and do chemical analyses to get the time. Problem is that we have multiple phases of metamorphosis. So for us, all you have to remember is that it's Paleozoic. Those metamorphic rocks have been like that for a long time. Okay? So they got metamorphosed, and then the dinosaurs came, and in the middle of the Cretaceous, the granitic rocks got injected. That's where the pulse of molten stuff got pushed into this area, and then stayed and slowly cooled. All right? And then as we come up closer and closer, the rocks that we see in Vasquez that I pointed out, which are angular, those were formed in the Oligocene about 28 million years ago. Then we have the conglomerates in the Pleistocene. The rocks that are here in the valley, the sedimentary rocks, are between 16 and 2.5 million years old. If you get newer than that, we have things they call recent alluvium, and that's just a stream channel that's dumping stuff right now. So those are the ages of the rocks we're looking at. So to make it simple, don't have any of the really old stuff here. We have the granitics, which are the age from the age of the dinosaurs, metamorphics from the age of the fish, and the other stuff, Miocene, Pleistocene. Those are basically, to really simplify and make it something that's approachable for the kids, that's about when the saber-toothed tigers were around. Okay? All right. So now that we know about rocks and minerals, let's look at what the Earth is here in the Placerita Canyon. What you're looking at is a drawing, which you would draw if you were standing up by the old Walker Ranch, and we're looking at a super huge bulldozer cut right across this valley, exposing the rocks down to a depth of about 4 miles. Okay? So on our right, as you're sitting here, on that side of the valley, when we look out, you'll see a really high white cliffs back up to the little housing tract. That is right over here. That is the Saugus Formation, and at the base of it is the San Gabriel Fault. Okay, that one's on your list of things you need to know. Okay, there's two. The San Gabriel Fault has split right there, but both of those breaks in the rock are considered part of the San Gabriel Fault. And then coming across to about right there, like maybe just about where the road is or directly under our feet, is the Placerita Fault. And the Placerita Fault is separating the TP, which is the Pico Formation, and its sandstones and conglomerates, Pliocene age. On that side is the Metamorphics. Okay. Faults are breaks in the ground, and the ground moves in one of two ways. The most common way for faults to work is it's either the ground is either being squished or opened up. As it opens up, then they have cracks form, and the one big chunk of the earth falls into that crack. When you go out across Nevada, you'll see a flat valley and then a mountain range. And then a flat valley and another mountain range. That's called basin and range, and that is because of that kind of formation. The faults are not purely vertical, so as you look at the fault and the rock's moving, usually this way, you'll have a side of the rock that's on above the tilting fault and a side below. This side is called the hanging side. Okay, so if the fault's doing this and I'm getting squeezed, it's going to squeeze the rock up. If it's getting pulled apart, then this is going to fall down, right? Okay, so the way they talk about that is you describe the direction that the fault dips into the ground, then you look that way, and the rock you're looking at, did it go up or down versus the block you're standing on? Does that make sense? Okay, so that's the most common kind of fault, and it's what they saw a lot of back east when they were studying the Appalachians in Europe. Everybody was happy. Then they came to California, and instead of doing this, who knows what happened, but now we've got rocks from who knows where smashed up against this. What in the world? It wasn't until plate tectonics worked that they understood why we have the strangeness that is Southern California. Okay? And into the 60s, if you were a geologist who was trained in California, you could work for the oil companies, but you didn't get to go work in Oklahoma because your sense of geology was twisted by the twisted environment you were trained in, and you never really got it properly. They sent you back to California. Okay? And that's because a lot of these faults that we're looking at here, that TP moved 20 miles along that fault to get here. Okay? San Andreas has moved much further than that. All right. So the things you want to know are fault right down the middle of the valley, sedimentary on that side, metamorphic on this side. The faults that we look at are the Placerita, the San Gabriel, and the San Andreas is the big one we all know of. It runs from basically the Sea of Cortez off past San Francisco and off into the Aleutians. We'll come back to that in a minute. All right. Fortunately, the San Gabriel is not regarded as an active fault. Yes? Question?
I was told that the reason that they have more deaths from earthquakes in South America is because the earthquakes go up and down, whereas ours slide. Is that true? Or like they can open up like movies and people drop through, but ours don't. Ours slide. Is that true? So
we have geology that's similar to their geology in North America, but I think it's probably much more truthful to say that the higher depth rates are caused by building codes than by the style of deformation and what happens to the Earth's surface underneath them.
It's probably somebody from South America.
There are differences in how the ground moves, and if we have time, I'll talk about it. But we're kind of running short, so we'll see. Otherwise, I'll be glad to answer questions later. All right. So those are earthquake faults. A fault is where there's a break, and then there's some offset. So which way? Okay, it's slanted this way. Hanging wall, foot wall. Which way did this hanging wall go? Up or down? Yeah. But then this one, hanging wall down. So this whole area here was being stretched. Okay, remember when I talked about stream channels and deposition? But when you're looking at things, you're trying to decide which way was up. Which way was up on this rock when it was deposited? Up was up even then. It's not always true. If you saw this shape and it was flipped over, then you'd know that this entire slab of rock had been flipped and it was upside down now. That's part of what we tell you. The other thing that geologists do in order to tell the timing of what happened is, okay, we had a dry environment. This is the calcite being deposited, and we deposited a bunch of sandstone, some more calcite, a bunch of water here for a short while. Okay, and each one of these things had to happen with this being younger than all of these. Okay, but then you have some cracks in here that don't cross everything. So you try and figure out which crack happened first. So like this crack probably happened after that crack because it can't cross it. So if you're a geologist, you have to try and recreate, put everything back to where it was when it formed, and then make a map about what all those things tell you about the shape of the Earth 200,000 years ago or 1 million years ago. Okay? All right. So this is why we have so much action here in Southern California. The Pacific Plate is the middle of the ocean. Up at the top, you can see the Aleutians. This is the Ring of Fire. Japan is over here. So currently, we have a big, huge Pacific Plate here, little tiny slab of a plate there, and this plate is going this way. Okay, but right here, I'm sorry, this plate is going this way. That plate is going this way. See if I can get it started again. So see, this is a spreading center, and that's why this is going this way, because it's splitting right here, and this part's going that way. So the relative motion of this part of the plate versus North America is different. This is going a different direction than this. And that's why when we get up to here, this thing is going in a different direction. It changes, when this hits, it starts to tear the San Andreas off. That's what you're going to see.
So where are we in that picture, Eric? Los Angeles?
We're right there.
Okay.
So right now things are starting to slide. See them slide? So, Sea of Cortez, us. All right. So when we talk about earthquakes and stuff, the kinds of earthquakes we have are the right slip. The kinds of earthquakes that'll happen along Portland, Seattle, Alaska, this portion right here, are more like what they have in Japan, which is not a good thing if your daughter wants to move to Seattle and you think about Fukushima. Okay, so plate tectonics. This is your kids, anybody over 3rd grade is going to have been exposed to this. Basically what happens is, we talked about the crust being thin. The crust splits for some reason because the asthenosphere is moving it. Where there's a split, new crust is formed out of the same kind of material as the volcano, the Hawaiian Islands. Hawaiian Islands are shield volcanoes, really flat because that stuff is not very viscous. When you look at the volcanoes in Hawaii or Mount Shasta or Mount Hood, they're shaped like this. That's because the chemical composition of the material is different. Why is it different? When the oceanic crust, which has been receiving water and other things as long as it's been chugging along until it hits a continent, gets pushed down. Once it gets pushed down deep enough, it melts. As it melts, the white stuff, the felsic material, melts first. It percolates up and out and creates a magma chamber. And that's why the Sierra Nevadas are mostly white with a little bit of black, and the Hawaiian Islands are mostly black with a little bit of white. Okay. The other difference is this stuff in the Sierra Nevadas, more granitic, is much more viscous. So, and it's got a bunch of water in it. So when a volcano like Mount St. Helens has been building up pressure for a long time, and it pops finally. It's like a bottle of champagne. The pressure is off, and the gases expand, and that accelerates the removal of material, which reduces the pressure, which causes the gases to expand, and blammo, you have a big deal. That was pretty impressive in Mount St. Helens, where we lost about 6 people. When Mount Hood goes, it's going to be a different story entirely.
Seattle, right?
Seattle. Yeah. Yes.
So is that why at Mount St. Helens you had the copious amounts of ash
Yep.
versus in Hawaii, you just have the lava flows?
Yes. That's why.
Yeah, Eric, could you, I've never been able to understand that term, pyroclastic flow.
So it's the rock foam with a lot of air in it that comes blasting out, mixes with other air to some extent, but it's still at 1,000 some degrees. It's denser than the rest of the air because it's got all that rock mixed in it, and it comes chugging down the valley.
But it's not like magma, it's sort of lesser viscosity.
Much lesser viscosity.
Yeah.
It's not a magma flow.
Yeah, it's mostly air and
Yeah.
okay.
Sounds like broken glass.
Yeah,
The
pyroclastic.
material, if it freezes too fast to form crystals, it's obsidian. Okay, so then they have, if you drive to Mammoth, you drive Bishop, and you drive through a bunch of white rock. It's that same kind of pyroclastic flow. It's now landed and welded together because it landed before it had a chance to solidify completely, so it welded itself together. It's called a tuff, but it's a result of a high viscosity explosive event that blew out Long Valley, which is where Mammoth is, and that's why they created a second exit from Mammoth. The scenic view out of Mammoth is because the not so scenic view might be gone when a volcano goes, if it goes. Yes.
So what causes the difference between the flat, shiny Pahoehoe
The-
and
The temperature.
The temperature.
So as you watch the last volcano go, the last eruption off of the Kilauea, the first stuff that was flowing was A'a. A'a is a name for basalt flows. They have basically 2 kinds, A'a and Pa'o'oi. If you look at the videos of the slowly moving flowing stuff, the crust on the surface, it forms a crust, and then that crust, while it's still thin and flexible, gets pulled along and it forms little ridges, and it looks just like coiled rope. Okay, so that's one form. If the stuff was colder when it came out and more viscous, it gets very clunky and you have big chunks of rock. And you can see these on the side of the road as you drive to Mammoth. And those chunks of rock on the surface then work their way along, getting carried and jumbled and tumbled as they go. And they are highly angular and tough to walk on barefoot, and that's how it gets its name. Okay?
Not true.
I'm out. Okay, so the other thing to think about is when we talk about tsunamis, is what can cause them. If you look at this area here, with this oceanic crust and this trench, that's being dragged underground. This side is being dragged with it, and when this cracks, it's like a huge flipper. Bing! And it'll have miles of distance, and it'll move feet at a time. That's why you have the tsunami that hit Fukushima that I was showing at the start of the class. And your warning time is very short, because tsunamis travel at 500 plus miles per hour in the open ocean, and they are full depth. Okay, so we've got, all right. So this is part of, again, Pacific Plate going off towards Alaska, parallel plate going in towards North America. Our houses to be are about right there. You can see how there's subduction. There was volcanism and basalt flows by Vasquez rocks at the time that some of this was happening. There's not any volcanism south of Mount Lassen now, unless Mammoth goes. Come on.
Mount Plain?
Damn it.
That video didn't make it into the...
Yeah. Shoot. Let's see what else it didn't make it. All right. That's too bad. That was really important. See about this one? Nope, it didn't make it good. All right. So what happens is, this plate's going like this, and then it's gonna, a spreading center is gonna come up through here. As that spreading center passes this point, the relative movement is gonna go from this way to this way. As it starts to move this way, it grabs things here and it tears them off the side of North America. As that tear happens, it's going to grab what will become the transverse ranges, the San Gabriels and the Santa Monicas, and twist it. Okay? So the rocks that we see here at this time are oriented like this, and then by the time we get to current time, they're oriented like this. That twisting creates the big bend in the San Andreas, and it creates the LA Basin, which filled up with so much soil. That's important to us in a couple of ways. This mountain range across here, in addition to being a source of significant seismic threat, creates the rain shadow and the wind shadow that keeps us having less smog in the LA Basin. Okay, and less rain. Rainfall in the mountains due to the lifting of the cloud, the moisture as it goes by, is many times as high as the rainfall we have here in the valley. For us, we don't have much rain falling gently in the valley. We have rivers that flow by. Let's try.
So if I remember correctly, when that land came around and came back in,
Mm-hmm.
that the French point was right here in Newell Pass.
Oh no, the twist is actually happening on the San Andreas further east.
Okay.
All right, so, all right, we'll skip that. It's not super important. What is important to us is, again, no video here, but look at the ages of the those dates up there, 1100, 1300, 14, 16, 18, 1857. Those are the dates of breaks on the southern San Andreas. So where we have the big bend, San Andreas Fault comes up, bends, and then goes up again. This section is the southern San Andreas, and it breaks about every 150 years. So what's 150 plus 1857?
1957.
Yeah.
2 years ago.
Yeah, so we are overdue for an earthquake.
Is that what said?
Sorry?
Is that what said?
It's the absolute truth. What's that?
Is that what said?
I'm so scared.
Merced's up here.
Oh.
What'd you say?
This is,
I'd be like running to the door right now.
this is Salt Sea. This is San
No,
Bernardino. This is San Bernardino. This is the LA Basin. We're right here. This is the Grapevine, Garland Fault, Mojave, Mammoth, Santa Barbara.
So the lesson is store more water at home.
And yeah, at the very least. So what you're looking at here is the trace of the San Andreas. You can see Santa Barbara, Lancaster up there. This is a scenario that was created by the USGS for a study by the state of California to prepare for earthquakes. Scenario is that the earthquake starts at the south end and runs to the north end. You're going to have a time frame here from the time that it initially ruptures until it goes. The color is the ground movement, ground velocity, and it's basically 2 meters per second. So the ground is going this fast. 1,002, 1,001, 1,002. And then we won't go that far, but that's how fast it's moving. Okay. Next. I know I put that in there.
There it goes.
Okay.
So great.
So you're going to notice a couple of things. Where there's mountains, it shakes less. Where there's valleys, it shakes more. The valleys, the analogy we use is the bowl of jello. And when you hit a bowl of jello, the bowl just goes bang and the jello keeps shaking. The longer you have shaking, the more it is a problem. The yellow at the front as it proceeds north is the actual rupture continuing, and the shaking you see in the LA basin there between Los Angeles and San Bernardino. You can see how it's still popping. Over by Palm Springs, Desert Hot Springs, it's still shaking 2.5 minutes in.
So where's Newhall on this, Eric? I see Lancaster. It looks like it just went right through Newhall.
Right, yeah, that's Newhall right there. Is it? Yeah, that's Newhall right there. So we are not as bad off as the LA Basin, but the shaking in some areas will last for quite a while. The Northridge quake, longest shaking lasted about 30 seconds. Longest shaking on record is from an earthquake, a 9 in 1960 something in Alaska. 9 minutes of shaking.
Oh, jeez. Continuous shaking?
Continuous shaking. There were people who just got bored with being terrified and sat on the sofa. It's either going to stop or it's not, and eventually it would stop. One of the things you can do to try and counteract the psychological trauma is say, stop, stop it, stop it. Eventually it will, and then you have control.
Shaking stir.
Okay. So here's the thing to think about that earthquake. That earthquake is going to have 27 feet of offset along the entire range from the Salton Sea to Lancaster. And it may actually end up being larger than predicted here because there are some folks now who think it could break and not stop at Coalinga. It could go all the way to San Francisco. Doesn't really matter to us because any energy released up by by Nipomo doesn't matter to us. We're too far away really to be affected by it. What does matter to us is we need the infrastructure of our lives: water, utilities, food, electricity, all of those nice things that get to us across that earthquake fault. And I don't know one of them that's going to survive 27 feet of offset. So think back to the windstorms they had in Pasadena about 6 years ago. Came down and took out all the electrical system. Took SoCal Edison 2 weeks to know the full extent of the damage. Not to get things back up and running for everybody, to know the full extent of the damage. And in that case, the damage was limited to basically the western San Gabriel Valley. They got help from Ventura, Oxnard, San Diego, you name it. Okay. Now, put that big an earthquake that's going to affect everything from San Diego to Lancaster, and how long is it going to take us to get help? How long is it going to take them to replumb the LA aqueduct? If you think that 3 days worth of water is enough, you are an optimist. Okay? So I'm not kidding when I say go ahead and get some supplies. The standard rule is 1 gallon of water per person per day. If you buy a case of water in the plastic bottles, that's enough for 3 days for one person. If you take that, stick it in your garage, and just rotate, use the oldest bottles first, you'll be fine. If you store the water for more than 2 years in those clear plastic bottles, it'll go bad. If you store it straight on the concrete, it'll go bad. Okay? But the reason that they started having firefighters teach the CERT classes is that we were going to be on our own. So if you want a real nightmare scenario, we won't go there. Okay. All right, so utilities are going to be knocked out, water's going to be very scarce, medical facilities are probably going to be overwhelmed, if not partially destroyed, and communications is going to be impacted. For communications, certainly cell phones have helped with that. For the text, it will be knocked down. Some people say that they expect texting to work, other people say no. They recommend the pessimists recommend you keep your landline AT&T type phone because those are self-powered and they will work even after an earthquake. They will not work immediately after an earthquake because once they get knocked, the phone receiver gets knocked off, it overloads the system and the system can't handle it. They shut off parts of the system until they get down to where they can actually handle the load, and then they bring back parts. And the first thing that's coming back up is emergency services. Okay, and then after that, then they're going to do payphones because that's an area that serves a larger portion of people. And then they'll go to citizens in various areas to try and get them to where you can use the phone. When you use your phone, you're probably going to be impacted. Your neighbors are going to be impacted. Your friends from work are going to be impacted. Your relative Aunt Joan in Illinois will not be, so you can reach her. So have a contact person out of the area everybody in your family that wants to clarify what's going on, update the status, contacts them, and then they check back. So you call once. This is what we did after the Northridge quake. We called when I knew that my in-laws were okay, to my sister in Portland, and then 2 hours later we got back. By that time, my brothers had all checked in, and we knew what was going on. So it gives you a chance. I didn't get a chance to talk to my brother directly for a day and a half, but we were busy. So things going on.
Eric, you're watching cable TV, and this irritating thing going, This is a test of the emergency system. What are they doing there? I mean, what are they testing?
That is, they're starting to get together. Two things. That is to let people know if it flash floods.
Yeah, okay.
And things like that. Okay.
Right.
And it serves a purpose. There are limitations with that, as we saw with the Santa Rosa fires. If I'm going to tell you time to get out of Placer Canyon, it'd be nice to tell you whether to go east or west. Mm-hmm. If you got a big fire and you don't know whether to go east or west, you have the problem they had in Napa, and they didn't tell people which way to go because they weren't sure which way to go, and then they were getting hammered later for not having godlike prescience and saving those people's lives.
Is that what happened in Paradise? All those people got killed?
No, Paradise, they built the town 150 years ago, and it just has small roads.
Oh.
And it was at night, small roads, lots of trees, really dry, big wind.
Just overwhelming.
You're right, though. I remember in the Silmar quake, all of those things in the San Fernando Valley were massively impacted.
Oh, yeah.
The freeway, the overpasses and whatnot, they were all collapsed. Hospitals destroyed, all those things.
So these are the things you want to be able to provide for yourself: shelter, water, first aid and medical treatment. Remember, medicines for yourself, glasses if you need them. Be able to provide treatment for yourself, food and family. Food, store the food so that it's someplace that you can use it. You want to have 3 kits, one at your office, one in your car. The office gets you from your office to the car. The car gets you from where you are, home. Home has a kit that'll help you last for 7 days. And you might want to have alternate places in case your home goes up in flames.
I have a question.
Yes.
What kind of kit or food would you store in your car? What?
For
in
food,
this weather?
granola bars.
Oh.
Just something like that. I know granola bars have a lot of sugar in them, but you're not going to care.
Yeah.
They've got pop tops now. You can put canned peaches in there. It'll be good forever. And it'll,
Even with the heat of the summer?
yeah, canned goods are going to be okay. There are some issues with water and plastics. As far as storing in your car, you can get Mylar packages of water or cardboard packages of water that'll have a 5-year shelf life even in a car.
They have canned water too.
They do, but that is ridiculously, phenomenally, absorbently expensive. Okay, so the dates are on. So this is from a little while ago. They teach this class here in this city, and I think it's $30. And it teaches you fire suppression, hazardous materials, disaster first aid, search and rescue, terrorism, disaster psychology, incident command. The difference between being a victim and a responder is how well you have prepared. The difference between a disaster, which is a really bad thing, and a catastrophe, which you cannot recover from, is how well you have prepared. And so that class is offered at least once a year here in Santa Clarita, and I highly recommend that people take it. All right, real quick, economic geology. Economic geology here, we already talked about the fancy rock, where he just loaded up chunks of metamorphic rock and took them off and sold them. Obviously, we also have in this area gold and oil. The oil's across the way and on the other side of the freeway, and what you're looking at right there is the geologic traps that held the oil. So in geologic terms, that's called a syncline, that's called an anticline, and this anticline right here is what captured the oil by Wiley Canyon. And that oil seeps up when you go for a hike at Towsley Canyon Park. That's what you're looking at.
It was yesterday.
Right? Yeah, really cool. Okay, so then you see these shapes of this pointing up like this. That is right here. So this is looking west from basically above, you can say we're a little bit south of us. And that, you can see, you follow these rocks across. See how these are all dipping down this way? And those are dipping down that way. That's creating an anticline. When you go out and walk in the hills, you can see right here, those bedding planes are pointed up this way. These are pointed up this way. And that's what helped form that valley. Okay? So when we talk about landforms, the underlying geology helps determine what's there. Gold veins. This is an example of a metamorphosed igneous rock that had cracks. Then hot water came flowing through. We had a good question. How in the world does water flow through and dissolve gold? Well, you put it under enough pressure and it's really hot and it can dissolve gold. And dissolve just a little bit of gold at a time, but that's a pretty good vein there for them to find. Most gold ore does not look that nice, so the process of separating gold from the ore is often a problem. But if you're using weathering to do so, imagine that this whole rock has weathered out and now that gold is washing down the stream. Gold is heavier than water. Heavier than most of the other rocks. And so everywhere that the river slows, the gold drops out first. So when you're going gold panning, you look for places where there are big rocks or a waterfall or something that would stop it, or the inside curve, and that's where you would expect the gold to have dropped out. And then you come in and you do your panning. Okay, that's the kind of stuff that was done here. When they found the gold here in 42, they basically had a year when they could, there was several years that they did it, but they did not last the whole first year, because you can't do placer mining with no water. You can't, it's really hard to do panning without water to wash it. So that limited things. If you read the history, there's a Santa Cruz Valley History.org, scvhistory.com website, and if you look through, you can see interesting things that happened. 1887, the locals were fighting somebody who wanted to come in here and do hydraulic mining, which just means blow the hill away and then work the workings afterwards. So this is the low impact green method, but you can see how much money he's making. And this is the way they did it in the Sierra Nevadas. There are whole hillsides, small portions of mountain ranges that are gone as they reshaped basically everything from Donner north with hydraulic mining. Oh, maybe this will work. Nope. All right, we're going to skip right over that. Okay, here's the faults in the area. So, important thing is there's the Santa Monica Mountains and the San Gabriels, and this whole area, as it came up, twisted to create this basin. But lots of faults that are of interest to us. Newport Inglewood is the fault that caused the Long Beach earthquake in 1933, killed over 100 people, including taking out a brand new middle school. That's why we don't build buildings anymore. When you see a building with metal plates across the top of the top floor, the wall next to the top of the roof, that's holding that building together so it won't collapse as quickly. For landforms around here, we don't have time. That's Vasquez rocks. You can see how the bedding planes are forming an anticline to our right, and we have differential erosion.
How do we know it's not a syncline to our left?
You would expect it to be both.
Okay, good.
That's the Saugus Formation on the other side of the San Gabriel Fault. And then the brownish cut face next to the road here is the Pico. Younger and softer, less consolidated. But all of those, the clasts, the bigger rocks inside the mud base, in both of those formations, are well-rounded because they've been transported for quite a ways.
Was that actually the fault face that you're seeing there?
I don't think that's an actual fault face, but it's very near there. The map I saw did not make it look like it was. There are other places where that style of rock supports a big face or a big cliff face without it being a fault face. Okay, so on the hillside behind me, you're going to see several processes that are both geologic and biological. You can see the plants that come in, they're trying to hold the hill up, but we've got sloughing coming down the hill, and the soft soil is being washed down to here. And the thing that we're going to try and build toward is pointing out that while we start out with hard rock up at the top, processes with animals, the FBI, fungus, bacteria, insects, all of those things are helping to break the rock down. Oh yeah, cool.
Fungus alert. This is the time of year to see fungus, okay?
Very
There's
cool
the fungus.
up here. You want to keep them out of the poison ivy if you can.
Yep.
But as you point out, what's going on as you pass here, you've got trees that have survived many fires, and you can see the slough now where the water is starting to move the leaves and debris. The technical term for this compost on the surface is called duff. That's what we call it, the fire service. And it's being washed off. But there's soil here that's supporting all of these plants, a great vibrant community. As we continue a little further up, we're going to see what's called bioturbation, the digging into the hillside, and it's by different animals, and you can use that to help them look at what's going on. This tree has some great fungus on it. I don't know what kind it is. Do you?
Yeah, we call it shelf fungus, like a shelf of a, it's a generic term for a whole group of funguses.
I'm a lumper. I like that.
Yep,
So
it's a lump.
So a shelf fungus there on that tree. Now when you're starting where I am, you can look at the cut slope above us and see the soil. That doesn't look a lot different than the sedimentary rock. It's not hard. Things have dug into it, built their home. So how does it look like that when I told you before this is all metamorphic? That's because it's weather. And we can talk about the processes that create that weathering. In this face, you've got three different kinds of holes. Above the three, there's one with a big flat bottom. On this cut face, there's some holes that are about the size of a little handball, racquetball, and then little tiny ones. The big one is for ground squirrels, little ones for gophers, and the little tiny ones are for scorpions. But you look at when I talk to the kids about these, look at how well protected those holes, those caves are, or dens for those various animals, because they're in amongst the roots. But now we've got a contrast between that development of a very deep soil and what we're going to find as we continue further up. The other thing that I do occasionally is talk about wildfires. This area, when I started here 10 years ago, all of this had been burnt out, and every oak in here looked like that one. But most of the oaks have come back. The overstories come back. Prior to that fire, you'd walk through here, and it's reported that the canopy completely covered it. And it's slowly working its way back. But even on the trail, you can see erosion happening where the water is creating its own channels and trying to take out trying to move things down from what we call the base level.
Occasionally you'll get questions about these wooden barriers, these wooden things in the trail. Have we talked about these yet? No. These are called water bars, and they're put in to get the runoff off the trail. The way they're supposed to work is the runoff comes down, hits the water bar, and then goes down off the slope so it doesn't erode the trail. Okay, so kids will ask about these, so that's what they are.
Yeah.
You can see that this one worked for a while, and then like most dams, it got filled up.
Yeah, these need to be maintained, and if you're interested, I'll introduce you to Jim Hazard of our trail crew, and they work on this occasionally.
Yeah, I was doing Counseling the other day.
Does anybody know what DG is?
Oh, yeah, you know those are.
Decomposing granite? Does this trail not look a lot like decomposing granite? Okay. The thing is, we're not in the granitics yet. What's happening instead is we're in an area where the metamorphic rocks have the same chemical composition. This is a bedrock exposure right here, but it's a bedrock exposure of a metamorphic rock, not a true granitic one. But it is weathering out in the same way, with the crystals of quartz being left behind by the chemical breakdown that weathers out the other stuff. Now as you walk along, looking on the side here, you can see some more metamorphic rocks, and it's got banding in it. Helps you identify as it. But in this, rather taxing if you're walking backwards 100 and some yards that we've walked through, we went from a soil development that was yards deep down next to the gopher holes, and now it's right on the surface, slightly weathered bedrock. But it is weathered. Roots can get in there, animals can dig in there to some extent, and that happens over time. One night walk with the kids through this section, because there's less I can do or can talk about. We've already pointed out most of the plants as we're going. I like to do a little bit of 20 questions. So they tell, okay, I'm an animal, and they get to ask, do you have a skeleton? Nope, no skeleton. Are you a bee? Nope. Do you have an exoskeleton? Yes. Are you poisonous? Yes. How many legs do you have? And they can use those things to work out what kind of an animal I am. And if we're walking downhill on this, I build up to the scorpions, which are in those little holes down at the bottom. Kind of keep them interesting.
Eric, can you give me a critique here of something I do with the kids on the trail here, geology? I pick off something I do with the kids. I don't know if it's correct, but Eric's going to critique me. Hold this. Thank you. These are the rocks that are along the side of the. I say this is a granitic rock, a decomposing granite. Is that? Okay.
No, this is still metamorphic rocks, so it's not a.
It's not. So this
You
is
can say it's a decomposing granitic.
a
But
decomposing granitic.
the thing I'm trying to stay away from is calling it a granite, which implies that it's a true igneous, when this stuff has all been metamorphosed.
So this is a metamorphic. Good, thank you. That's point one. So you can say this is a decomposing granitic rock, okay? And what you can do to have fun with the kids, because there's sometimes not a lot to do here, I break it up into sections, and you can take a piece. There's plenty of this, okay? And then I hand it to the kids, and I say, here, everybody take a piece of this, okay? Everybody take a piece of this, and then you got your fancy gloves on.
Okay.
But, okay, and do this. Try to crush it in your hands, okay? Crush it in your hands, and you guys are strong. You're like Superman. You can crush rocks in your hands. And what do you have left? Sand. You have them dump it on the trail, and then you can talk like Eric. Where does this sand end up? Has anybody ever been to the beach? This washes down to the creek and to the beach. So what do you think, Eric? Is that an okay story?
Yes.
Good. I paid him, by the way. So. He gets paid with all other volunteer instructors. So.
It's got to be nice to you, huh?
So standing right here on this ridge, if you look, well, we're not gonna be able to walk up there because the group's too big and it's hard to get. But right on the top of this ridge, there are rounded rocks that are unlike these. They are straight out of the stream bed. So how did they get on top of a metamorphic rock? This whole area. No, not a flood. It was buried. It was lifted up. It was buried, well, either lifted up or eroded away on that side. And it left this little, it's called a pendant of rock up here. And the only way that you can tell as a geologist how it got there is to crawl through the bushes and look at the contact between the two kinds of rock and go, okay, is it hot? Was it melted? Is there slick and slides from an earthquake? I mean, a fault or a landslide? And then you can decide, okay, that's how this thing got here. So
So you're saying it was lifted up?
I'm saying this area was lifted up since those were deposited.
Right.
Or this entire valley was full, and I'm going more with this was a slightly different elevation. But it was kind of surprising the first time I went up that trail, and I was expecting metamorphic rocks, and all of a sudden there was a bunch of rounded cobbles. Okay, so Superman type strength over there, we can break a rock. Here, 100 yards away, it's going to take a little more grip strength to break this stuff. There's a couple things there about the rock that are geologically telling. It's got, if you look along here, there's a preferential break. And that could be offset, but I think it's mostly that area is where there was more of the dark mineral, and the darker minerals weather out first. So one of the things that came up earlier in the coffee room was how does Dudella, or some of the plants that really grow, finds that little tiny crack, and it's able to take off. The amount of damage that can be done by a root is truly phenomenal. In this environment, we don't get much cracking due to ice. In order for ice to work as a cracking agent, it has to get really cold, because as it expands, it has to freeze and go down to, let's say, 0. When it goes from 0 back up to 32, it's going to expand, and that's what's going to cause pressure. But the more pressure you have, the more likely the water is to melt. That's why ice skates work. So you have to get really cold and have extra cold pressure in order for the ice to actually apply that expansive pressure that's going to cause things to crack. The roots, on the other hand, are very efficient. They draw out the minerals to help encourage the weathering, and as they grow, they create more pressure to help break the rocks. Okay, so now we've got metamorphic rock up here, and you can see, looking at the stones on the ground, this stuff hasn't been transported at all. And we're going to look out that way. The mountain's on the skyline with a little bit of sun. Thank you. With a little bit of snow on the top of the topas coming back this way, and you can see bedding laying in just to the left of the 2 high tension wire towers. That's bedding planes. They're laying this way, so probably an anticline that way and a syncline over here. The Newhall oil fields in Placer Canyon are right on the other side of that freeway. You can just see the freeway through the bottom of the pass. Disney's just around the corner. Not a geologic feature, but it'll be interesting. And then as you work our way back, metamorphics on this side, sedimentary rock on that side. That's where the fault comes through the middle. That fault also controls the orientation of this valley. It is not normal for water to flow off a hill and then turn right and go this way, and that's what this stuff did. It came down Sand Canyon, turned left and headed off this way to rejoin the river. That's all fault control through here. Created a zone of weakness that was then eroded away.
So the difference on the 2 sides, is that because the fault has been moving things this way?
Yeah, that stuff is going that way. Okay, and that goes back to when we look at the rocks that are inside the bedding planes over there. When you look at this stuff, it's granitic. When you go a little bit higher, at a different portion of that same formation, it's rocks from a sedimentary / metamorphic source. And so it moved from one valley where it was drawing off of one mountain range and got slid along. As it was still forming the rock and filling up the valley got moved and now it's getting sourced from another place. And then you can tell that as you go through time into another section of the rock. So when you go down, we call it down section, older and older rocks, then you find different things that are happening. So these rocks over here basically happen on land. It's called a terrestrial environment, and it's interfaced in an east-west range with the formations that are underlying tiles of the canyon, and that stuff was just off the ocean. So over time, my fingers are terrestrial, marine, and the sea came in or the sea came out. So at this time, water level was a little higher. This time, water level was a little lower. The boundary between the two moved back and forth over time. But when you get here, it's fairly apparent now. The grass is making it a little harder to see that this is these road cuts here are the classic layered birthday cake look of sedimentary rock. So it helps the kids identify what they're looking at. Okay. Yes.
Yeah, she wasn't here today. She usually comes in late, but I don't know what happened to her today.
I'm not sure about that.
Lexi, Trisha is the one up front.
Okay.
And Alexia, she usually comes in late. But I didn't see her today.
Yeah, well, I noticed it too. I've been trying to talk to each person.
Good, thank you.
I want everybody to feel at home.
That's what we try to do.
She always says I'm an ambassador anyways.
Yes. So the question here is on this exposure, you see some coloring and it's red. Almost all of the red that you see in geologic environments is a result of iron being weathered to rust. Rust gets a special name in geology, it's called hematite. But that's what makes things red. Geologically, one of the reasons that we have the big steel mills back in the Great Lakes area is that during the time that when the planet first formed, there was no oxygen, which was good for life, because if there's oxygen, it oxidizes the molecules, the organic molecules that are needed to be the building blocks of life. Life was able to start, and then we had a bunch of oxygen. Oxygen arrived as it was being introduced into the atmosphere. It went over then and rusted all of the hematite that was around, and that's why they have the big iron beds. And those iron bands back there in the Earth's column are what provided the source for those steel mills.
Ah.
So kind of cool thing.
The wreck of the Edmund Fitzgerald, huh?
I don't know what he was hauling.
Oh, iron ore. I thought the song.
Okay, could be.
As the big ships go, he was bigger than that.
That's the one.
Those songs here.
Okay, so who's really good with math? Who can tell me how much water is inside this water tank?
I think they learned that already.
Okay, you deserve a cookie when we get back down. Okay, and try and get the kids really good with math, try and figure it out. Yeah, it's here because getting rid of it's a pain in the neck.
When was there water in it? How long ago was there water in it?
Oh, probably, I don't know. I think probably they abandoned it sometimes in the 60s or 70s when they brought the domestic line up from Newhall. So this was the original water supply when they built the park back in the 50s. And I think the domestic water came up from Newhall sometime in the 60s or maybe early 70s. So
I learned that on my twilight hike.
it's been abandoned for a while.
Toilet hike?
I went on a twilight hike.
Oh, twilight.
Oh, you heard the story, yes.
Sorry. Too much rock and roll, I don't do it.
I thought the same thing. So.
Yeah.
You can look that number up on the website of DWP, and it's listed there.
Is it? Well, you show me the website. I've never been able to find it. Send me the link. No, it's a LA County inventory tag, and so Jim says it's on a website. So send me the link, and we'll have that information for everybody.
So while we're up here, I want to talk about a couple of things. One is another place that we have access to that's pretty cool with history is Ellesmere Canyon. And if you walk in there, I've got a lot more of it after I looked up the Santa Cruz Valley history stuff. They had an earlier version of the LA Aqueduct that now goes through from Castaic. And there used to be an aqueduct that went through that area. And some of the ruins of that construction are still in that area.
Actually, there still is part of the active aqueduct goes through there. Dan Cott, who worked for DWP, which you guys haven't met yet, but I was surprised there was kind of a excess cover, and you could what's that all that water down there? So that's an interesting area.
A lot of water.
Yep, lots of water.
Yeah, I forget. I think it's a 50-foot or
It's huge,
35-foot pipe that's under the ground there.
buried, but
Phenomenal.
you're right on the. You can see on the SCV history website they have pictures of that. Yeah.
Yeah. Okay, so the other thing that I do is firefighting, and I've given some talks here about fire behavior, and the challenge for everybody is, for me, it's I want to take my crew home safely, and then save your house if I can. For you guys, it's I want to make sure that guys like me can save my house. So that it comes down to fire behavior, and fire behavior is all about fuels in the area. Whether or not they're fine, well, how much fuel is there, whether or not it's going to burn easily, and what the carrying capacity of the fire is going to be when it gets here. And when we do those analyses, as a responder, we are more aware than most of the fact that the nature of the fire changes depending on the time of day. So as we stand here right now, the sun is to the south, you can see shade on most of these hillsides, sun is to the north, lots of bushes, not many bushes. Okay, that is purely a result of the fact that we're in the northern hemisphere, and the sun shines more on the south-facing aspect. In order to show the kids how that works, just take your hand, make a V, pointing east or west, and you can feel the difference in temperature on the sunny palm versus the shady palm. Okay, so if I'm a firefighter and I'm trying to decide whether I can make a stand here, my threshold is based on how big I think the fire is going to be when it gets here. If it's over 8 feet, I can't fight it even with a hose. If it's over 12 feet, I probably really want to be someplace else when it goes by. But if I'm assigned to come protect this precious water tank at 2 in the morning, and I come in and I look over there and the fire's not doing much, I go, oh, well, I'm fine. Well, when it decides to burn over here at 2 in the afternoon, that's a different story. And I need to predict what the fire is going to be like. So when people talk about, well, how could they have let all those terrible things happen? The wind changes over time, and then the aspect of the fire changes over time, and the amount of fuel changes over time. So the firefighters will talk about coming into alignment. If it's uphill, it burns 16 times faster. If there's a strong wind on it, it can push it even more than that. If you have high fuel load like this, it'll burn longer, but it'll spread more slowly. If you have light, flashy fuels, it'll travel through more quickly, which means I have less time to get to where it's safe. But I don't have to have my safety zone be as big in order to protect me when it's there. So I look at all those things, and then you look at the sun, because right now we're at about noon and the sun's straight up. As it goes over, those faces are going to heat up. This morning, this face heated up. So again, if I'm trying to figure out what's going to happen, I look at the geography around me, which way the sun's climbing. So the last time in Glendale that we burned somebody up, the fire was over there, he was on a slope like this, everything was good, then the sun came around and heated up this slope, and the fire came around to here, and he was expecting the fire to come from that side, and it didn't work out so well for him. So all of those things are things that the firefighters are supposed to figure out as they come in and guess, what's the weather going to be like 2 hours from now, 4 hours from now, 6 hours from now. So that those are the challenges that they face. For you, since you're worried about your home under the worst of conditions, you don't need to guess what it's going to be like 2 hours. Just go, what would happen if? What would happen if the fire got here 2 in the afternoon, Santa Ana winds, do I have enough fuel separation? And the thing that people are learning now with code changes is that it's not the flaming front that's rolling up the hillside that's taking out your home. Most of us have 30 feet of separation, and 30 foot of flame length is really unusual. It's the embers. In the Thomas fire in Ventura, they lost an apartment complex 2.5 hours before the main body of the fire got there. The embers had been blown that far ahead so that it landed in and got inside the building. And the main weaknesses of the structures, sometimes it's vegetation, but often it's ember intrusion into the attic space. So how many people here live in the interface, which means where there's brush near their home? Okay. The main things that you want to try and do to harden your home is remove flammables from near the house. Don't have a big wood pile right next to the plate glass window. And control the vents that go into your attic space. You need the vents to get into the attic space to get the hot air out. But during a fire, if the screens are not big enough, if the screens are not fine enough, then the embers get in and they blow in and land inside the house. And then everybody goes, wow, it's great, we saved all these homes. And they drive down the street. 15 minutes later, it's not so great for your house. Okay, so a bag over the, and this would be a heavy bag, not just a trash bag, over any vents, and tape things across the underside of your vents, and it'll make a big difference on your survivability of your home.
I hate to put you on the spot, but I'm going to give you a typical question docents get. A little kid will be, there's always one that picks up rocks. Okay, and so I'm going to be the random kid. He hands me this
We
rock.
told you not to pick up rocks. What if a snake had bitten you? Come on.
That's a good, I like that. Remember that. This rock. Okay, I'm looking at this rock, and I would say this is mostly quartz. It seems to have that broken glass plane on it, and maybe the red is a little bit of the iron, hematite. Am I sort of right or not?
You do have some iron in there, but if you, yeah, that's heavy good quartz. I'm trying to find some crystals. Right there. That's a feldspar.
Okay. So what would you call this? A feldspar?
I would call it a felsic rock that has both quartz and feldspar.
Okay.
The feldspars are the white stuff that has flat surfaces on it, and then tell them how to look for it.
Okay.
So they can try and find it. And that is, you've done a great job. That is the most common mineral in the entire planet, and you just found it.
Good. Because usually I simplify this for most of us. If it's white, call it quartz, and you're probably going to be right.
Statistically, if it's white, call it feldspar.
Feldspar.
If it's clear, call it quartz.
Oh, okay. So, thank you. That's good to know. After all these years, so you can still learn stuff. Okay. Feldspar in German is field rock. I think
I believe,
Caroline told me. Okay.
Yeah.
Okay. And then that kid will pick up like sort of a black rock. Now, is this like?
I told you to stay away from the snakes. Don't you listen?
Yeah, cool. Is this a mafic rock with hornblende and stuff?
Yes.
Okay.
And again, when you look at the little black ones, you can see crystal faces if you rock it, and you can see them in there. And it is really hard. Can't do that with most sedimentary rocks.
So this is a metamorphic rock.
This is a metamorphic rock, and it is non-granitic because it has so many dark minerals in it. It does not seem to have much mica in it, so it's like a hornblende.
Okay, good.
So, but easy. It's a mafic igneous rock formed inside the earth after being very, very hot, and it re-solidified.
You remember all that?
Sure. Far inside the earth.
Tens of miles.
What?
Tens of miles.
Okay.
I'm struggling to remember how many tens of miles.
In years?
How many years?
Yeah. I
Thousands.
would think people would ask that.
Well, all the rocks here were from the dinosaur ages, the metamorphic rocks from the dinosaur ages.
Okay, I was just reminded it's noon, so we can continue to stay if you want to talk some more, or if you need to get back.
Am I getting time and a half?
You get time and a half, big guy. If you want to go, it's probably better to go back that way. You can go down this way, but you'll have to cross the creek and get your feet wet, or walk down along the creek. But one thing I wanted to show you before we go. This is our Harbinger spring, okay? The hoary ceanothus. Okay, hoary leaf ceanothus is starting to pop all over the park. If you remember this plant and tell your friends, they will be amazed and amused, okay? So thank you, Eric.
Sure.
Thank you.
You're welcome.